Welcome back from your break. I hope you've been thinking about all those questions that I asked you about the relationship between theoretical probability and relative frequency. And I hope that you can see that we can use maths, possibly, to make some predictions about the future. It all depends on how big your data set is. It all depends on how many experiments you do. And so that's why I get excited about this particular topic of probability, because it's so relevant and it's so real. And even though we're doing silly little experiments like spinners and dice, it can apply to so many more things that we can see around us in the real world. And so we can make predictions, not just about the weather, but we can make predictions about the health systems, we can make predictions about climate, all if we collect data and we start to look at what the possible outcomes are and what the potential desirable outcomes that we're looking for. So let's have a look at our concept map again. And just to remind you, we have focused quite a lot on theoretical probability. And so you should know by now the probability of an event that we would like to take place is the number of times that event can happen divided by the number of total events that could also happen in a particular situation or scenario. Then we did some real experiments with a spinner. And what we recognized here is the key word is relative frequency. And you need to be very clear that relative frequency is very similar to probability in the sense that we can say relative frequency is equal to the total number of outcomes that we've got, that we've done in our sample. So these are the number of things that we're wanting, divided by the total number of trials. So that's the total number of trials, not the total sample space. So you can see we can do many trials. The more trials we do, the closer we get to the theoretical probability. So what I thought we would do in this little last section is to try and combine these two ideas by looking at a very simple experiment and use it to explain those terms and make sure you've got them. So let's talk about rolling a dice. Now, I'm sure you've all seen a dice. You know that it's usually a plastic cube and it has 6 sides, so it has 6 numbers on each of the sides. And so the first question is, what is the sample space for rolling a single die? We say the singular for dice is die. It doesn't mean fall over, okay, and not breathe. A die is just simply one of those cubic things that have numbers on them, okay? So please be aware of that. So what is the total number of sample space? It doesn't depend on the size of the die. It is asking you about the numbers in the set that we can have on the side of a die. So the sample space is made up of these numbers. It could be a 1, it could be a 2, it could be a 3, or a 4, or a 5, or a 6 for this particular type of die. Now, if somebody said to you that they rolled a die and they got 8, could it be in this sample space? Well, no, it can't be this type of die. This type of die only has those 6 numbers. 1, 2, 3, 4, 5, and 6. Can't be 0, can't be 10. Now, there are die that are able to have those sort of numbers, and they play them in all sorts of games, but we're talking about a conventional die. And we recognize that there are only 6 possible answers from any trial or any experiment that makes up the sample space. Be very clear about this. The number in the sample space, that's the sample space as I've drawn it out. The number in the sample space is indicated as 6. So there's a difference between showing you all the numbers, the set of numbers that are possible, as compared to counting the number of options there are in the sample space. Be very clear about the difference between those. But I had asked, what is the sample space for the rolling of a die? And that's the sample space given as a set. The set, we use a curly bracket and then we list the numbers. There are other ways of doing it as well, and we're going to see about those a little later. Now, let's look at the next part of the problem. And the problem is, what is the probability that when you roll a die, it lands on the number 4? Now, guys, this isn't that difficult, because actually we've only got one outcome. So it's really not difficult to see that the desired outcome here, the favorable outcome, is going to be the number of favorable outcomes. The number of favorable outcomes is for the number of 4 to be the answer, favorable 4. There is only one. There's only one possibility of, this isn't a fancy trick die that has 4 painted on 3 of the sides. No, it's got a number 1 on one side, a number 2, and so on. And so there's only one favorable outcome. And so if we were to recognize that there is only one favorable outcome, but the number of possible outcomes out of the sample space is 6. So what's the probability of us getting a 4? The probability of getting us a 4 is going to be the number of getting a 4, the number of possible ways of getting a 4, and the number in the sample space. And if you do that, you'll see it's 1 out of 6. Now, we can leave it as 1 out of 6. We could even say it's a ratio of 1 to 6. We could also calculate the percentage, and that's what I'm going to do here. I'm going to say, let's get our calculator out, and we're going to say 1 divided by 6 is equal to 1/6. We put it into a decimal, 0,1666, and it carries on and on and on. We have to round it off. Often they ask you to calculate to a certain number of decimal points. In this case, if they said 2 decimal points, we would say it's 0,167 as a decimal. But if we wanted this as a percentage, what would we do? That's right, we'd multiply it by 100. So we're going to take that, multiply it by 100, and if we were then to make sure that we do the 100, we'll get that, and as the answer, it's 16,67%. So this is exactly the same as 16,67%. That's the probability. We've now shown that we can use different formats to get the probability. Guys, there's one last little thing that I want to tie together. Is it always going to be 16%, 16,67%? In reality, is that what's going to happen? Well, we're not too sure. We know if we increase the number of experiments or trials, then relative frequency will get close to the probability. It could be bigger or smaller than the relative frequency, but, the relative frequency could be bigger or smaller than the probability, but they'll get closer and closer depending on the number of trials. But here's some data that we've got that we were given for a particular experiment. We're told that a die is rolled 48 times. Now, that's quite a lot of times to roll a die. And in the counting of the number of times the die has been rolled, the number 4 appeared a total of 5 times. Okay? So they say to us, what is the relative frequency of observing the die land on the number of 4? And you're asked to give your answer to 2 decimal places. So please don't get confused. When they ask for relative frequency, they're not asking for probability. The calculations might look similar, but they're not identical. So please be very careful that you understand and that you give your appropriate notation when answering. So let's go and take the data down and make sure that we've got it right. So if we say relative frequency is going to be the total number of trials, and we're going to divide that about the number of outcomes. So the number of times that it got to 4. Because that's what we're really wanting. We're wanting to find what's the relative frequency in this experiment, which had 48 trials. How many times did it get onto 4? Well, I've given you away some answers. The number of trials was 48. So the total number at the denominator here is going to be 48. The number of times that it landed on 4 was 5. So we get that the relative frequency of this little experiment is 5 out of 48. Now, guys, we can leave it as 5 out of 48, but the question didn't say that we should do it. It actually gives us an instruction. And here's a very important thing. Whenever you're doing a maths problem, you've come to an answer and you think, yeah, I've got it. Just go back and read your question, because in the question, look what it says. Write your answer correct to 2 decimal places. So it means calculator time. I've got to get out the calculator and do that calculation. So here we go. Remember, that was the probability. Now I'm going to use the calculator to work out the relative frequency. I'm going to say 5 was the number of times that it landed on 4, and I'm going to then divide this by 48. And I'm going to say 5 divided by 48 is equal to 5 out of 48. No big surprises there. But look what it says this is in terms of a number. 0,10416. Now I need to write it to 2 decimal places. So remember, I look at the 3rd decimal place here, and the 3rd decimal place is a 4. So be very careful that we're going to write this as an answer of 0,10, because I'm not going to round up. So let's just make sure we're in the right place to give our answer. And we're going to say that the answer to this, correct to 2 decimal places, is 0,10. What do you think it would be if we were asked for a percentage? Instead of a decimal place correct to 2 decimal places, what would the percentage be? Well, I don't think it's that difficult. We have to multiply that by 10. So the percentage, in terms of relative frequency, the percentage relative frequency would be 10. And if we used the decimal places as well, then you would be able to see it would be 10,42. We'd round up the 1 to a 2, and we'd be able to say 10,42%. That would be the percentage of the relative frequency. So guys, can you see that when we did the calculation for the probability, it wasn't that this wasn't the same. It was 16%, where here it's only 10%. What's that indicating to you? Well, I hope you can see that 48 isn't a big enough sample space to allow the relative frequency to get close to the theoretical probability. We'd have to do a lot more trials. And if you do a lot more trials, overall, you'll find that the relative frequency will get closer and closer to the theoretical probability. So let's just wrap up everything that we've done during this particular lesson, because I think we've explored some interesting ideas, and perhaps we're in a situation where we can answer our big question. But let's quickly go through a few ideas in our summary. So what is probability? If you had to use an everyday word could be chance. Now, what is the chance of something happening? It could be absolutely certain. Then you would say the chance of that happening is going to be 1. If it's impossible, then the chance is 0. The probability would be 0% of that happening. We define probability as the total number of favorable outcomes divided by the total number of possible outcomes. We've defined that very carefully. We've defined the formula for probability of a particular thing happening as the number of times that A would happen divided by the number of things in the sample space. And in a similar way, we've calculated relative frequency to be equal to the number of times that A happens divided by the number of trials total. We recognize the more trials we do, the closer those two numbers get together. And so I want you to make sure that you construct your concept map and remember these two things. When we're doing probability, always think about theoretical probability and experimental trial. Don't go away. Make sure you join us again the next time we have an opportunity to explore this wonderful world of probability. And perhaps one day we'll be able to answer the question, can maths help us predict the future? I hope you'll be part of the answer too.